Neo can now walk, climb stairs, pick things up, and do real chores all on its own. 1X's new Redwood AI runs fully on board, controlling the whole body and learning from both success and failure. It moves like a human, handles messy homes, and adapts on the fly. In-home trials are already live, and mass production kicks off in the year 2026. This isn't a test. 1X is building robots for your living room. First off, Redwood itself. Under the hood, it's a 160 million parameter vision language transformer. Small by today's gargantuan large language model standards, but purposely trimmed so it can run entirely onboard Neo's embedded graphics processing unit at roughly 5 Hz. That matters because you don't want your vacuum fetching bot to freeze whenever the Wi-Fi hiccups. Redwood meshes 3 data streams, sentence-level language embeddings distilled from an off-board speech-to-speech model, visual tokens from a pre-trained vision transformer, and a proprioceptive history that tracks every joint angle and torque Neo feels. Those streams flow through extra transformer blocks until they're squeezed into one latent vector, and a diffusion policy then expands that vector into the exact joint commands for either the bipedal Neo or the older wheeled EV platform. Cross-embodiment by design, yet still tuned for the humanoid form factor, which is pretty slick. Painting-wise, Redwood gorges itself on a huge data set of tele-operated and autonomous episodes recorded inside 1X offices and employee homes. Variety is king here. The couch keeps moving. The coffee table shows up in new spots. The dog toy changes shape. The model has to find a water bottle it has never seen, maybe wedged under a chair it has never visited. So the data pipeline deliberately scrambles object identities, lighting, and clutter. On top of predicting the next action, Redwood tackles so-called cognitive heads. It tries to guess where its own hands are in the camera frame, map the outline of nearby objects, and flag anything that might matter for grasping. Those auxiliary tasks ground the vision features and stop the network from overfitting to the exact layouts in the training set. What's wild is that 1X also feeds Redwood failure rollouts. When the robot botches a pickup or bumps a cabinet, the cognitive heads still get a learning signal, turning every blunder into extra supervision rather than dead data. Now, because households aren't tidy workbenches, 1X had to make Redwood drive every inch of the body at once. The model spits out synchronous commands for the arms, the hands, the pelvis pose, and the walking velocity, so Neo can lean into a heavy door, brace an elbow against the wall, or switch hands mid-carry without waiting for a separate locomotion planner. That fusion unlocks mobile bimanual manipulation, where the robot glides across the floor while simultaneously balancing a kettle with one hand and nudging the fridge shut with the other. Everything stays on that single 160 million parameter graph, which is why it still runs in real time on the graphics processing unit tucked behind Neo's knit torso panel. All of that would be theory-heavy fluff if the legs couldn't keep up, so let's roll over to the new reinforcement learning mobility controller introduced on 11th of June. Historically, teaching a biped to walk took months of tuning handcrafted shaping rewards to make the gait look remotely human. The 1X team ditched most of that guesswork. They start with a low-level controller trained entirely in graphics processing unit accelerated simulation, randomizing mass, friction, and sensor noise until the policy is robust enough to transfer to the real robot. On a desktop RTX card, the basic stand and walk routine now trains in under an hour, which is kind of ridiculous. But early reinforcement learning, walkers shuffle like video game non-player characters, so 1X layers in motion capture references. They capture real humans, strolling, jogging, pivoting, even dancing, retarget that to Neo's joint limits, and make the reinforcement learning policy follow the tempo while juggling balance. The outcome is a gait that flows naturally in any compass direction, forward, backward, or sidestepping between a sofa and a coffee table. Sidestepping matters because kitchens and living rooms love to trap a wheeled robot in diagonal corridors, and a biped can simply shuffle sideways without pivoting in place. Still, a single motion capture clip only teaches one choreographed path, so the engineers split the brain in two. There's a high-level kinematic planner that turns coarse inputs, think joystick vectors, or Redwood's own walk, that A-way signal, into a synthetic but human-looking trajectory. Then the low-level reinforcement learning network tracks that trajectory while monitoring ground contact forces. The split gives smooth transitions. Redwood can order a quick left shimmy, then a long diagonal stride, then an in-place swivel, all without ragdolling halfway through. Stairs got their own highlight because households have them and most factory floors don't. Neo's stair mode relies entirely on stereo red, green, blue, so no LiDAR puck sticking off the head, and no time-of-flight depth module on the chest. The stereo pair pumps raw images through a convolutional neural network that infers a local height map that blends with proprioceptive history so the robot knows where its feet ended up a split second ago. Thanks to domain randomization during training, the controller is cool with mixed height steps and even sideways traversals, so if the staircase includes a quirky half rise halfway up, Neo just compensates. And if a task pulls the robot down to carpet level, scrubbing a stain, packing the bottom drawer, the same reinforcement learning stack can ease the bot into a kneel, a full sit, or a prone lay down, then stand back up without external help. The engineering payoff is obvious. Redwood can learn vacuum under the couch maneuvers because the underlying controller actually lets the torso fit under the couch. There's a short but fun demo tying everything together. Engineers fine-tune Redwood on a simple soccer ball dribbling task. The vision module tracks the ball, Redwood predicts whole body joint targets plus a pelvis velocity, and the reinforcement learning controller translates those into ground reaction forces. The ball rolls, the robot glides after it, taps it with the instep, repositions, keeps dribbling, no remote joystick mid-sequence, and the same pipeline supports teleoperation when needed. A human can still pick up the reins through the action interface if the AI goes off script. Voice interaction sits on a thin off-board layer. A speech-to-speech large language model, you can guess which one, converts the spoken request into a clean text command. An encoder embeds that command into a vector, and Redwood ingests the vector alongside its vision and proprio tokens. Because only the embedding travels back to the robot, latency is shaved and everything else stays offline friendly. Redwood's onboard graphics processing unit carries the main inference load, so if the homeowner's router collapses, Neo still places dishes on the shelf. Only brand new voice queries stall until the link reappears. Safety stems from redundancy too. Every NeoGamma unit ships with soft knit outer panels and compliant actuators that yield before your shin does, plus a live teleoperation fallback where operators can jump in whenever the autonomy stack flags uncertainty or something looks sketchy, keeping both the customer and the dataset intact. Let's talk chores, because that's why anyone wants a home robot. Redwood already covers the basics: sorting dirty laundry, vacuuming rooms it has only rolled through once, watering indoor plants, making a pour-over coffee, folding t-shirts, hauling grocery bags up to 19 or 20 kilograms, that's about 44 pounds, and opening the door for the delivery driver. The cognitive heads feed into a retry strategy. If the first grasp slips, Redwood shifts grip and goes again rather than timing out. Over time, the system keeps refining since the AI learns from both the success and the miss, so each household run turns into fresh training data. And because the manipulator commands and the walking commands share the same transformer, Redwood decides automatically whether the left, right, or both hands should do the lifting based on where it plans to step next. Coordination looks almost theatrical, but is completely dataset driven. These capabilities aren't just lies. 1X built a giant booth at NVIDIA Graphics Technology Conference in San Jose this spring, and Neo ran demos almost the whole week. Granted, the public routines were still teleoperated for reliability, yet the hardware showed endurance. Same actuators, same proprio sensors, no hydraulics, just electric torque transparent motors. Internally, in-home trials have already started with company employees. The field robots record how real apartments change day to day. Fresh laundry piles, kids' toys moving randomly, and that constant churn should make Redwood's generalization even stronger ahead of a wider beta. Failing plans sound ambitious. Chief Executive Officer Bernd Bornich says the company wants to push into full manufacturing by the year 26, initially shooting for around 100,000 units per year, with a stretch vision of eventually making humanoids in the millions. Obviously, that hinges on supply chain sanity, battery advances, and enough capital, but the roadmap exists. On pricing their mum, which hints consumer models are still a couple of iterations away, yet the team claims the learning curve is pointing toward affordability once volume ramps. Competition is heating up too. Figure AI over in the Valley is polishing its Helix system and has BMW in the loop for factory pilots, plus a logistics partner lined up, Tesla's Optimus project, aims for 5,000 robots next year, despite reorganizing after Milan Kobach left. Their bet leans on massive internet video pre-training. Unitree Robotics and China just restructured into a joint stock outfit so they can go public. Their H1 humanoids is already starring on national news. What separates 1X for now is a home-first focus. They engineered Neo for door frames, coffee tables, and that awkward space between the fridge and the wall, not for conveyor belts or warehouse pallets. The soft exterior, the compact shoulder width, the voice-first interface, and the compute-efficient 160 million parameter model all aim at living room dependability rather than industrial throughput. Will robots like Neo replace housework, or will they replace us? Let me know what you think. Don't forget to like, subscribe, and hit the bell so you don't miss what's coming next. Thanks for watching. See you in the next one.